Hey everybody, welcome to Activity 7.1. What is sound energy? Now, if you're watching this video, it's probably because you're looking to get the answers and you've already gone through the self-paced activity. Um, if you don't know which one I'm talking about, well, it's this one. So this is probably what you're going through. And you might have been absent, but you're still going to go through this and it's going to guide you through Activity 7.1. And at the very end, there is a link here, Answer Key and Scientific Principles. That's what this video is going to be about. So our learning target is we're going to learn about how sound energy is different from other types of energy. So you've learned about, kinetic energy and gravitational energy and elastic energy and thermal energy, and now you're going to learn about sound energy. So when we think of sound energy, think about, it's hard to even imagine where you don't hear sound. Can you think of any place where you really don't hear sound at all? But sound is all around us, and sound is an incredible thing. So you're watching a video, but you can't see me, but you can probably figure out what I'm doing right now. What am I doing? If you said bouncing a ball, you're exactly right. Even though we could not see it happening, you knew it was happening. You could tell me how many times it bounced. And by the sound of it, you could even probably tell what type of ball it is. You can probably figure out it's not a basketball, it's not a racquetball, it's a tennis, not a tennis ball, but it's probably some different type of ball. And you can start to figure out what type it is if you were to rewind and listen to it again and again. So sound is pretty powerful. Now, when we think of sound, sound is associated with the motion of air molecules. Just as thermal energy is used to describe the kinetic energy associated with the motion of particles in an object, the term sound energy is used to describe kinetic energy associated with the coordinated back and forth movement of particles. And it's these particles, the air particles anyway, that go into our ear and we can actually pick up as sound. So if it's organized or if we have experience with it, like a ball bouncing, we can figure out what is happening even though we don't see it. So let's get started with the answers, because you've already worked through the guide and you've already answered everything. So this is just going to, this video is designed to help make sure you get the correct answer so you have the correct answers for the test. Cool. So consider how sound energy is involved in making things stop. Most drums typically have sharp sounds that fade away quickly. Those that fade away slowly usually have mellower sounds. So let's start to explore this. And you watch the videos. So when I refer to the videos, it is these videos right here that you watch and this one that you watched as well. So when I talk about videos, I'm referring to those. So the first question is, what happens to the skin of a drum when you strike it, and which way does it move? So you saw this in the videos, and you saw that they vibrate back and forth rapidly with the vibration dying out quickly. And some of the videos you watch were in slow-mo, but you could still see that the drum skin was vibrating back and forth until it died out, which actually happens pretty quickly. So hold on, just make sure there's nothing underneath here. Okay, so the next set of questions. So now we're going to be doing those part 1 questions, and you actually started part 1 up here, and this is the next set of questions. So what does the drum skin do to the air molecules around it as it vibrates? Well, it makes them move by striking them as it vibrates back and forth. So as that drum skin goes up and down, it's actually moving the air molecules in an organized way. So when those air molecules make it to your ears recognize the sound. When does the air around a drum have more kinetic energy, before it was struck or after it was struck? Well, of course, it was after it was struck. It's not going to have any KE if you're not striking the drum at all. So the air molecules have more KE after being struck by the drum skin than before. And where does this kinetic energy of the air come from? Well, the kinetic energy of the air was transferred to the air from the drum. So the increase in the air molecules' kinetic energy comes from the drum skin. So if the air is getting energy from the drum, What should be happening to the energy of the drum? Well, think of the scenario with the basketball and the tennis ball that we had. When we put the tennis ball on top of the basketball actually bounced less because it transferred energy to the tennis ball, which actually, in some cases, actually hit the ceiling in this room. So the same thing can be concluded here, that since Ke is being transferred from the drum skin to the air molecules, the amount of kinetic energy in the drum skin decreases as the kinetic energy of the air increases. So as the drum's vibrating back and forth, it's transferring its energy to the air, and because it's transferring energy to the air, voila, the energy of the drum is getting lower and lower and lower, and then boom, it stops. So if the drum skin's energy decreases, what should happen to its vibrations? They're going to get less and less. They're going to decrease. They're going to get smaller and smaller, however you want to put it. And again, you can paraphrase all these answers, put them into your own words, make sure they're correct, but also remember that you can use these on the test. So how can we tell this is happening? Does the drum skin stop vibrating, or does it keep going? And there's actually two different ways you can see this. So first of all, because the sound of the drum is transferring its energy to the air, it's actually going to die out pretty quickly. Here I use the word rapidly because the sound the drum makes rapidly dies out. So we're going to hear that the energy went somewhere because it dies out rapidly. Where did the energy go? To the air. And the other thing you could do is if you were to lightly touch the drum skin a second or two after striking it, you're not going to be able to feel it vibrating anymore. It's not going to be vibrating anymore, or more than likely it's not going to be vibrating. But if you were able to touch it right as you're hitting it, you would feel the drum skin vibrating. So you could feel it. It's probably the lesser of the two, but you're more than likely going to hear that the drum dies out rapidly. And then which drum makes the sound that fades away faster? One that makes a loud sound or one that makes a more mellow sound? Why? Well, typically a drum that makes a loud sound will fade away faster. And why? Because it transfers all of its energy very quickly to the surrounding air, making a loud noise. But then there's no more energy to transfer, so the sound stops quickly. On the other hand, if the sound is not as loud, it means that the drum is transferring energy more slowly, so the sound will actually last longer. So now we're in between. Those were the part 1 questions. And again, sound is what we hear with our ears as a result of the air moving in a coordinated manner called a wave, a sound wave. When something makes the air molecules all move together in a coordinated manner so that they do not actually move far from their positions, the result is something we call a sound wave or sound vibration. When this wave gets into the ear, it's detected, and a signal is sent to the brain where it's interpreted as sound. Sound waves can actually be felt on the skin as well. If they are loud enough, people who are deaf can actually feel the sound vibrations, although they can't hear the sound. So let's get into the second part 2. What other devices do you know that make sound energy? I just put a few here: bouncing ball, ringing bells, boiling teapot, subwoofer, springs, toys. I don't know. I can't think of too many things that don't make sound. Even like paper, if you were to take it and you were to crumple it up, it's going to make sound. Wind, you can hear wind. So there's very few things in this world that don't make any sound. It'd probably be harder to come up with something that doesn't. Where does the sound energy of a bouncing racquetball come from? Well, it gets a little bit more technical. So as you're dropping that racquetball, the GE is being converted to KE, and then it touches the ground, and then that KE is being converted into EE. You also have some thermal energy as it's coming down. Those types of energy are being converted into sound energy. So it's being transformed into sound energy. So it's really a transformation versus a conversion. So some of these are conversions, but then it's going to transfer energy from the ball, in this case the racquetball, into the surrounding air. So especially if you consider it two different systems. Does this sound energy have something to do with why the ball stops bouncing? Yeah. If it's got sound energy, where did it get the energy? That energy had to have come from somewhere. So there's actually less energy to keep a ball bouncing if it makes a lot of sound. Draw an energy transfer diagram. Remember, energy transfer diagrams are going to be squares. So here's kind of generic. A bouncing ball, you got KE, GE, EE. So this is one of those things that this is what the book has. And I would question a little bit. One, they didn't have the environment because they were supposed to have what it's being transferred into, or maybe you put the air. Is it really going to be an EGE? Well, that GE gets converted to KE, and that KE gets converted into elastic energy. And it's right then that it actually makes the sound. That's bouncing. So it's when it hits the ground. So if it hits the ground, is it really going to have any GE right now? Again, I'm not going to get that picky. This is what the book has, but I would start to think, well, is it really transferring GE to that? Is it definitely elastic energy, definitely kinetic energy? And there's that sound energy, and it's going to transfer it into the environment, the air in this case. So go ahead, copy this down. It's another good example to have for the test. So that does it almost for the questions. I've got the making sense question coming up, but I want to go through the scientific principles quick first, just to explain a little bit before we get to that final answer. Remember, sound is associated with the coordinated back and forth motion of particles. And that's why usually when we think of sound, we're going to associate it with kinetic energy. And when an object emits sound, it loses some of its energy to the surroundings, which makes sense. That's why things stop. So now for that last question. Hopefully you watched the video, and hopefully this makes sense then. Why, when pop, does a fully inflated balloon make a louder noise than a partially inflated balloon? Well, it's easy. The material in a fully inflated balloon. So if you think of a balloon, if you blow it up and blow it up even more, it's getting bigger and bigger and bigger, so that it's stretching more. It's going to have more elastic energy. And because it has more elastic energy, it's going to make a much louder noise when it's popped. And think of it as, say, a rubber band. If you pull a rubber band back just a little bit, stretch it a little bit, it's not going to fly very far. But if you pull that rubber band back further and further and further, it's going to fly further and further and further. So when a balloon is popped, its elastic energy is transferred into the sound energy. The more elastic energy you have to begin with, the more sound you get. So the fully inflated balloon is going to make a much louder sound than a partially inflated balloon. So hopefully you got all your answers correct. Hopefully everything's good. Hopefully it looks good. So if I go in and take a look at it, it looks like you did a quality job and you get credit for this assignment. As always, if you have any questions, make sure you ask. Bye.